So, good morning, ladies and gentlemen. My name is Petra Murinova, and I'm chairman of this session. For this session, there were prepared 4 talks, but the last talk was cancelled, so we have only 3 talks, and the first talk will be given by Karel Fiala. It's joint work with myself, and the title of this talk you can see on this table. So please, you have 20 minutes for this talk.
For some, we have also two active one in the some people or if we have these 4 forms of identifiers and study the property of them that are mainly can this sketch which is called the classical position which describes properties with identifiers. So we form of what does this control so in our case to quantify if false. The other hand up are that means that both can be false but both can contradictory. It means that both cannot be true and both can be false. So altern one which is altern form that it must be true. Altern is at the same time the super altern must. Now we have quantifiers and these. Now we put the inference. Generally, immediate inference that we one quantifier try to another quantifier precisely from the value of the quantifier that we can use not only but one way some structure of opposition. So case let us know that we know children like chocolate is. We know that all children like chocolate is A, carry with quantity which is we can infer that no children like chocolate is false, because contrary means that so this must be similarly we can that some children like chocolate is all time children like chocolate is. That was our motivation, so use the classical case, and our goal of this talk is to pass this immediate inference logic, and we will extend the classical approach in several ways. We will add intermediate modifiers, almost there, but modification was proposed by Professor Novak in rationalist positive theory. Instead of using classical square of opposition, we will use graded some square function was by similar. And also we extend the true values from 1 0 and 1 over and 2. Let's go to some definitions. So the definition is as that is what is that? Means that we take some subset from subset S and we that we take element that in its degree of membership of zeros, that means we don't take it. So in part we measure the start formula and we evaluate it by some evaluative expression. We put in definition concrete qualitative expression and obtain these quantifiers. Again, we denote by capital letters. Here we can see classical ones. One of the one, almost all, most many, and each has a multi-element form. It's multi-form of almost all. It is almost all, so we will be sometimes we need to work with quantifiers with presuppositions, so we need to slightly modify the definition in that way, and as essential import, and we then put concrete evaluative expressions and the similar quantifiers, and we then by capital letters. But now to emphasize the presupposition, we use and for these quantifiers, we can study the properties of subaltern contraries, subcontraries. For that, see that for subaltern we use the implication, which wasn't like there, so it's Lukashevich implication. Five line. Subaltern property. That the property between quantifiers, but and we are does it mean? Is based subcontracts Lukashevich addition. Use them both for contradictories. For subaltern, we use this inequality. We can modify this equation using the definition of Lukashevich multiplication or addition in the following way. And in the rest of the talk, we will focus primarily on the property of contrary of subaltern. So we can see that we can modify previous property to this inequality. So if we know true value of quantifier P2, we know that if we know truth value of quantifier P1, we know that the truth value of P2 will be less than equal as 1 minus truth value of P1. And basically for subaltern, we have the still same, so there is no change. But of course, we can modify in the same way by using the definition of Lukashevich addition and multiplication properties of contradictory and subaltern. So now we can move to the inference part. So inference part, I will record, is based on that I know the truth value of some quantifier, I know the properties, and then I will infer the truth value for the new quantifier. So let us show on the example. So let us know that quantifier P, which can be expressed by this quantifier. So almost all seniors realize that false news spreads quickly has truth value P, where P lies from interval from 0 to 1. It's like a real interval. Therefore, we know that the P is contrary to E, where E is no seniors realize that false news spreads quickly. And then using the previous inequality, we obtain that truth value for E will be less than equal than 1 minus P. Similarly, we can do like P is in some relationship with the other quantifiers. So we can do for all the possibilities. So we know that P is the contrary to E, B, D, G. So the truth value will be less than equal than 1 minus P for them because it's contrary. By A is superaltern of P or P is subaltern of A. That means that true value for A will be less than equal than P. And for T, K, I, their true value is greater or equal than P, and it's due to the subaltern. We directly, the quantifier P is not like connected to quantifier O, so now we can tell anything about its truth value. Now let us put the concrete value instead of P. So for example, we have the still same example, but now the true value is 0.9. Still the P is contrary with E. That means using the inequality which was presented before, we know that the truth value of E will be less than equal than 1 minus 0.9. That means it's less than equal than 0.1. And since the interval of truth values is from 0 to 1, that means that the true value for E will be from interval from 0 to 0.1, which is like very small truth value, so it's nearly false in every way, a possible way of possible value. Similarly, we can do it for all other quantifiers. So for the B, D, G, it's the same because it's still the contrary relationship. Here for A, due to the P is subaltern, so the truth value will be less than equal than 0.9. So it's from 0 to 0.9, which is a really wide interval. So that's not much good information. But for T, K, I, we obtain interval from 0.9 to 1, which is quite a narrow interval. So we know that the true value for this quantifier will be quite high. And we don't know nothing for quantifier O, so the true value can be anyone from the interval from 0 to 1. And if we try to use the other properties between quantifiers, we can get the true value for quantifier O a little bit narrower, and it's due to the using contradictory, but still the truth value will be from 0.1 till 1, so the interval is still wide, so it can be true, it can be 0.5, it can be 0.1, so still we don't have that much information. And finally, the concrete example in some reality should look like this. So there was 1.9, and there will be truth values for other quantifiers. And that's all for me. So to conclude this talk, in this talk I presented like the idea that from the truth value of some quantifier we infer a truth value of other quantifiers based on the properties of the graded Peterson of opposition, but it can be done for other structures of opposition such as hexagon of opposition or cube of the opposition. And also there are other possibilities how to do immediate inferences such as conversion, obversion, and contraposition. So future work is to study them and also study like their connection to the structures of opposition, but also to syllogism, because it seems there is some connection. So I think for the project, and thank you for your attention.
Thank you for your talk. So now we have time for discussion. Are there any questions? So please.
So my question is actually about this graded scale proposition applied to small models or small sets. In that case, necessarily some of its quantifiers will coincide. What happens to this contradictory in the other relations between quantifiers? Do you just aggregate all of them?
I don't understand your question, maybe.
So my idea was when we look at these different quantifiers on smaller sets, then there aren't enough quantifiers to make all of these distinct. When you only have a set with model with like 3 elements, almost all will maybe coincide with many or with most.
Yes, that's
in that case, these relations between different quantifiers, you just add them all up, or what happens to these relations?
I think in that case, that's true that, for example, for 3 elements, it would be like all, but I think for 2 elements, it would be like almost all, and probably also the most. But there are still contraries, so I think there wouldn't be change.
Okay, thank you very much.
So thank you for interesting talk. I am wondering if I assume that the restriction is crisp, no fuzzy, is crisp. So the whole evaluation of the fuzzy quantifier is based on the evaluation of the measure. So you consider measure, you have some evaluation of this measure using some function. So these evaluations must play some interrelationship between between them, because otherwise you cannot prove some contraries and contradictories and so on and so on. And I'm wondering, so if you are trying to estimate, and it's very easy, of course, and if you are trying to estimate, for example, some intervals, maybe I wonder if you cannot consider like interior and exterior, crisp fuzzy set, a crisp set of the fuzzy set to find some estimation where for the fuzzy restriction the result could be. So, for example, if I have some like restriction is fuzzy, so I can cover it by crisp set. So maybe I can get like very easy the information where the restriction is like a normal fuzzy set. So the core is non-empty. So I can take this core like the interior crisp set. And again, I get very simply where the value is for that. And because the fuzzy set is between this interior and say exterior crisp fuzzy set, maybe I can estimate where the result will be. And so because
maybe it can be done, but it's more
because it's very easy, because this is just the value of the
so basically take some like low some bounds,
like
and the fuzzy is between
estimation for the position of the fuzzy quantifier if you consider fuzzy sets, and maybe it could give you some intention or something like this one where you are.
Okay, thank you. I will.
It's just comment. Sorry.
Yes.
Okay. Thank you very much. So thanks once again. So thank you. So we continue with the next talk. Next talk will be given by Cerman Zbigniew, and the title is The Maximal Set of Non-Isomorphic Lattices Represented by maybe delta matrices preserving 0-1 aggregation. So you have also
Thank you. Today, I would like to introduce our concept about representing finite lattices using matrices. Of course, we are not the first one, but in the previous articles, we found the authors, they don't represent any finite lattices. Based on this representation, we can then aggregate finite lattices. For now, we aggregate only one lattice, and based on this paper, we can aggregate more and more finite lattices. So my presentation is divided to these 4 parts, from definition of delta incidence matrix to the number of all n-element lattices. In between, we ask questions about the minimum and maximum 2 lattices. In other words, aggregate 2 finite lattices, and lattice of all n-element lattices. So let's start with the term from graph theory. This is incident matrix, and its definition is very easy because the number 1 is only for 2 comparable elements in the lattice. Thanks to the finite lattices, we already know some rows and columns in the incident matrix. For example, first row, first column, last column, and main diagonal. So that means the all finite lattice is represented only by parts below main diagonal and above main diagonal. However, we can place 0 below the main diagonal. That means we get delta incidence matrix that represent any finite lattice only by the part above main diagonal. For short notation, we can use upper delta matrix, which is the important part above main diagonal. So based on this definition, this idea is proved by this proposition, which said that elements in any finite lattice we can label by the distance from the least elements. Based on this, we can use only this part from above main diagonal. So some examples. 2-element lattice, and this is its delta incident matrix. 3-element lattice, and this is its delta incident matrix. Both of these matrices are very trivial because these matrices don't have the important part above main diagonal. So let's move on to the 4-element lattices, where we have 2 options for delta incidence matrices. And we have 2-dimensional diamond and chain. So immediately we have first question. Exists one-to-one correspondence between all finite lattices and all delta incidence matrices? For the answer to the question, we take a look at another example. So for all 5-element lattices, we use these delta incidence matrices that have 3 positions in the important part above main diagonal. That means we have 8 delta incidence matrices. So let's start. First matrix represent 3-dimensional diagonal. Second matrix represent pentagon. Third matrix represent also pentagon. Fourth matrix also pentagon. We can see 5th matrix, 7th matrix, and lastly 8th matrix. On purpose, we skipped 6th matrix because this matrix violate the transitivity of the order relation. So this is problem. Okay, answer for the question 1 is no. We have 2 reasons for that. First, there exist matrices that violate the transitivity of the order relation. And second one, exist different matrices that represent same isomorphic lattice. So we have to remove these matrices, and we get this set of all non-isomorphic 5-element lattices. So question 2, how it look like minimum or maximum 2 finite lattices? Or in other words, how we can aggregate 2 finite lattices. So for the minimum and maximum, we use this very simple definition, which said that 2 delta incident matrices we can order by the elements on the same place. So for this set, we have this lattice, which is lattice of all 5-element non-isomorphic lattices. So immediately we have question 3. If we take all n-element lattices, do we get a lattice again? So for the answer, we take a look at the 6-element lattices. So again, we have this general form of delta incidence matrix. We see 6 free positions. So there are 64 delta incidence matrices. So let's start. First matrix represents 4-dimensional diagonal. Second matrix, third matrix, fourth matrix, and fifth matrix. We can see that we construct matrices by the number of ones. On the other hand, of course, between these matrices exist wrong matrices. For example, these matrices represent isomorphic lattice, or this one, or these matrices violate the transitivity. So this matrix we have to remove from the final set. So let's continue. 10th lattice, 11th lattice, so matrix, another lattices, and another wrong matrices, because these matrices represent isomorphic lattice. Interesting fact is that lattices 610 and 611, so this one, are representing only by these matrices. Okay, we have another wrong matrices. We can continue with the next matrices and next lattices, and so on. So wrong matrices, we can see wrong matrices that violate the transitivity. And now we encounter to the third problem for the matrices, because this matrix doesn't violate the relation, the transitivity of the relation, and doesn't represent finite lattice. This matrix represent only posets. So this is bad for us. So this matrix we have to remove from the final set. So let's continue. Another matrices, another lattices, and another wrong matrices, and the last one is chain. So if we return to the question 1, we have to add new problem for the delta incident matrices. So from the entire set of all delta incident matrices, we have to remove all matrices that violate the transitivity of the ordered relation. We have to remove all matrices that represent only poset. And the last one, we have to remove all matrices that represent isomorphic lattice. The third problem is very hard because if we take all matrices that represent same isomorphic lattice, which matrix is the right one? We don't know. But computer do. Yeah? Computer find the right matrices. So we have these 15 unique non-isomorphic lattices. So let's continue with the question 2. Now, again, we do minimum or maximum 2 lattices from this set. For example, we take lattice 644 and 646. So if we take this lattice, and we do minimum, the result is this matrix, which is not a lattice. So the problem is, if we aggregate 2 lattices, we cannot do a lattice. So this is problem. Okay. So the new question and the main question of the paper is that we want to find the largest subset that is closed under meet and join operation. Generally, that is closed under any k-array 0,1 aggregation function. This is computativity complex problem because we find only the largest subset for 6-element lattices and smaller one, of course. So this 13 non-isomorphic lattices is the largest subset that is closed under meet and join operations. And if we take these lattices, we get this lattice of 6-element non-isomorphic lattices. So if we return to the question 3, do all non-isomorphic lattices form a lattice? No. No. But if we take some subset, then of course we get a lattice. On conclusion, my presentation, we can briefly see on the number of all n-element lattices, which is, I have mistaken this, which is 2 power this number. So 2 power this number is upper estimate for all n-element lattices. For example, for 10-element lattices, we have 268 delta and matrices, but only less than 3 millions are useful to us. But in these matrices, there are posets. So this is 2 very hard problem, how to remove these matrices. This upper bound can be better, but this is only our hypothesis that for 11-element lattices and the bigger one, we can upper estimate of all n-element lattices by this number. So our future plans are, firstly, we want to create meet and join matrices based on delta incidence matrix. The second one, we want to create construction for the largest subset that is closed under meet and join operation. And the last one, we want more focus on the 0,1 aggregation functions and find largest subset that is closed under 0,1 aggregation function. Interesting fact, I proved yesterday that this set for 5-element lattices and this set for 6-element lattices, they are closed under any k-array 0,1 aggregation function. So these sets are very beautiful. Okay, some references were the first article I mentioned on the beginning of my presentation. And this is all. Thank you very much.
Thank you very much for your talk, and thank you very much for your examples. It was very, very nice. So, are there any questions or comments?
Means that it's very hard to say if the matrix is, for example, transitive, or the transitivity is very hard to prove from the property of the matrix, like the composition of the matrix is submatrix of the original one or something like this.
No, find matrices that violate the transitivity is easy.
It's easy.
But posets and isomorphic lattices is very hard.
Yeah. Thank you.
When you found this largest subset that forms a lattice, is this unique for the case of 6 and maybe in general?
I don't think this lattice find computer based on Python program. And
Okay.
I think that these sets exist more, but the 13 is the largest one.
Okay.
We don't found the 14 for the 14 lattices.
So there might be multiple with size 13.
Yeah.
Okay. Thank you.
Thank you very much. So, thank you once again.
you.
We will continue. So, we have the last talk of this session. This talk will be given by Kalafut Yurai. Yes, okay. So the title we can see here. Okay, thank you. So you can start. You have 20 minutes.
Okay, so thank you for introduction. I will be speaking something about smooth associative aggregation functions on finite lattices. So just it's starting to vibrate, so it's somehow it's get me out. Okay, so we know all what are finite lattices. So just for the notation, we have infimum and the supremum or meet and join. Since each finite lattice is also bounded, we have immediately the top and the bottom element. So it's necessary for definition of t-norm, t-conorm, and so on. It's for our purposes the interesting one. And I would also put your attention to discover relation, which is only a specific case which can occur here in finite lattices, that we have an immediate predecessor or successor of an element. Okay, so we know that the element lies next to each others. And this is not possible in the uncountable case, but in the finite case, it's the easy way to define the lattice only by discover relation. So, and we will stick on this notation. So just to let you know, and the notation for intervals is used as usual. So the preliminaries, from now till now, the classical aggregation theory is based on the unit interval. And the unit interval is really nice structure. Yeah, it's robust. We have infinite cardinality. We have topology and continuity and many other things, and also the linear order. However, when we go from the unit interval on these finite lattices, we lose all of these properties. So naturally, we have to develop other tools and other approaches how to deal with this. And first of all, the problem is the continuity, because we don't have natural topology that is suitable for this case. And thankfully, this was already doing Mayer and Torrens in 2005 in this paper for triangular norms. And they proposed the four different aspects, and one of them is divisibility, which only means some kind of surjectivity, because the continuity and monotonicity implies some surjectivity. So they think of something like that. And if I remember correctly, on Tuesday, it was extended also for more general settings. Then we have intermediate value property, which is also known from basic real analysis. So I don't think I have to bother you. Also, one which is property was one of them. It was on the finite chain, so there are some specifics, but I think we all could get the idea. And the last one, which is the most important in my talk, is the smoothness. And therefore, I was insisting on this cover relation because the idea is pretty simple. That this function has no jumps. Okay, so if we go from the element that lies next to each other, then we either stay in the same point or we move only at the one. And that is a natural assumption in many fields. For example, if I want to pass this button, may I borrow, to Ratko, I could either throw it, but it's from glass. I don't want to do this, so I can pass it by neighbors, and it's the safest and the natural way. I do not need the surjectivity that it has to go from all of you, but just step by step. And many is known, but mainly on the chains. And that's the problem. And I will try to persuade you that the situation change significantly when we go through to finite lattices. So first of all, okay, I forgot just the notation. All the T norms and null norms are defined as usual. And I use the prefix pseudo for non-commutative version of these classical operations. And finally, I put here also semi-T operators. It is hard to define them on finite lattices, but there were some trials that are somehow problematic, and they were trying to impose surjectivity instead of continuity, but it's still in the process for a few years how to define them on finite lattices, but it is as you will see, and I will try to mention also that. So what is already known, as I said, the majority of works was done on discrete chains. So first of all these four properties for T norms specifically are equivalent. Okay, we either got one of them or no, all of them or none of them. Then, if we have they were also characterized via ordinal sum of Lukasiewicz T norms, so via ordinal sum of smooth Archimedean T norms. And this is the back, okay. Then similarly as on the unit integral, we cannot obtain proper smooth uninorm. And finally, smoothness of pseudo T norms implies immediate commutativity. All these holds on finite chains. And after this presentation, okay, maybe only maybe I will try to show you that none of these, except the point of two, holds on finite lattice. So smooth T norms for smooth for T norms on finite lattices, we immediately obtain that divisibility smoothness are totally different properties. However, the intermediate value property implies both. Yeah. And here we see a simple lattice, which is always another chain, and the T norm, which is smooth, but not divisible, and divisible T norm, which, however, is not smooth. Yeah. So immediately as we accept the existence of incomparable elements, we obtain something like that. I will skip this slide just briefly. That we can also think of idempotent, and then we idempotency, and then we immediately obtain infimum. But to have this smoothness property, then L has to be lower semi-modular lattice. And also there is a problem to define on some specific lattices smooth idempotent functions because of the length and so on. So there are some peculiarities which aren't done yet, but that's the main idea of this slide. And also unlike the case of chains, we have smooth pseudo-T norms which are non-commutative in strict sense. And here is an example of one. So we mean this brings us to some kind of non-commutative logic, which is somehow stronger due to this smooth property. However, if we impose also divisibility, because they are distinct, as was taught, we'll immediately obtain commutativity. And also, smooth uninorms, they exist, but we have to go to specific finite lattices, such as this one. Okay, so here we have the diamond, and this is the induced by this such a uninorm. It's the simplest one. And I will try to somehow explain how smooth idempotent uninorms CA work like. So first of all, if we have U idempotent, then we have to impose these properties of lower and upper semi-modularity on the underlying sets. And also we can show that if U is idempotent, then U is immediately a null norm. When it is not idempotent, there is a problem because the smooth T norms on finite lattices weren't studied yet. We only know some things on them, but we do not know how they are characterized, and they pretty much affect the structure of the uninorm, and therefore I would like to see that this holds also for all smooth uninorms, but I cannot claim that yet. But from the Lukasiewicz T norms, and when the E0E and E1 are chains, that it seems that it holds. So maybe it will hold also in general. And let's say something about smooth idempotent null norms. Not only that all idempotent uninorms are smooth uninorms are null norms, but every idempotent smooth associative functions is null norm, which somehow reminds us of chains and unit interval. And the structure of idempotent null norms depends strongly on these subsets. And what they want to claim, just to take the points from incomparable a point of incomparable elements with the annihilator, and look on the infimum and supremum, and just took, this is for example the AXY, here is A01, and so on and so on. And when we have an idempotent null norm, then on this structure, it somehow induces a new order, which is only which is isomorphic to lattice, which is a Cartesian product of 0A and A1. But the order, the first order remains is reversed, and the second one is reversed. Yeah, we see here that it's reverse order here, and it's the classical order on the right side. And from this, it is possible to characterize and work with these smooth idempotent null norms, because if we got in this sense a maximum element of the set, then all the sets lying below have to be non-empty. So in the case of uninorms, where there is a neutral element in the top, in this top, all sets are non-empty. And finally, it seems that the structure of these, in the case of smooth idempotent null norms, is pretty simple. They usually have only one element possible, but there are some there might be some exceptions, so I'm carefully to claim it in all, for all points. So, and that was the main idea. However, this field remains open because we do not know nothing about the non-idempotent cases for T norms and eco norms at first, because on them depends uninorms and null norms. And then what happens when we drop the commutativity case? Okay, will this happen? What happened with null norms, also with symmetry operators? Okay, where we can define what are the lattices where we can study these smooth associated aggregation functions, because we have some, like, the idempotency does not allow this study. And also, this was what will happen if we drop the commutativity. And is this possible to say that all smooth associative aggregation functions are symmetry operators, as is in the case of the unit interval? Maybe, maybe not, but we will see. So I just want to stress that this field is not is very different from what is known, and I thank you for your attention.
So thank you for your talk. It's very nice. We are in the time. So are there any questions? No? Okay. I'm sorry because I'm not a very good expert in your area. I don't have any question for you. Maybe later in the community. Okay. So let's close the session and enjoy your lunch. Thank you.
Yeah.